Hello. My name is Jordan Thomas, and today I'm going to be talking about Border Gateway Protocol, or BGP. This is a project I'll be doing for my network class from the greatest school in USA, Harvard. Just kidding, OSUIT. Hi, Mr. Struther. Let's get into it. So, what is BGP? Well, Border Gateway Protocol is a standardized exterior gateway protocol designed to exchange routing and reachability information among autonomous systems on the Internet. The protocol is classified as a path vector protocol. The BGP makes routing decisions based on paths, network policies, or rule sets configured by a network administrator, and is involved in making core routing decisions. BGP may also be used for routing within autonomous systems. In this application, it is referred to as Interior Border Gateway Protocol. In contrast, the Internet application of the protocol may be referred to as Exterior Border Gateway Protocol. Let's keep it moving. So, the history. Where does this thing come from? Starting off, the current version, BGP4, was published as RFC 4271 in 2006. After progressing through 20 drafts from documents based on RFC 1771 version 4, RFC 4271 corrected errors, clarified ambiguities, and updated the specification with common industry practices. The major enhancement was a support for classless interdomain routing, or as I like to remember it, CIDR, and the use of route aggregation to decrease the size of routing tables. IPv6 BGP was first defined on RFC 1883 in 1995, while BGP4 has been in use on the Internet since 1994. The new RFC allows BGP-4 to carry a wide range of IPv4 and IPv6 address families. It is also called the multi-protocol extensions, which is MPBGP for short. Let's keep going, shall we? Operation. Okay, so BGP has these neighbors called peers. These are established by manual configuration among routers to create a TCP session on port 179. A BGP speaker sends 19-byte keep-alive messages every 60 seconds to maintain the connection. Among routing protocols, BGP is unique in using TCP as its transport protocol. When BGP runs between two peers in the same autonomous system, AS is referred to as internal BGP, or IBGP for short. Sounds kind of like a Apple product. Anyways, when it runs between different autonomous systems, it is called external BGP, or eBGP. Routers on the boundary of one AS exchanging information with another autonomous systems are called border or edge routers, or simply eBGP peers, and are typically connected directly, while IBGP peers can be interconnected through other intermediate routers. What else? So, extensions negotiations. Alright, so during the peering handshake, when open messages are exchanged, BGP speakers can negotiate optional capabilities of the session, including multi-protocol extensions, and various recovery modes. If the multi-protocol extensions extends to BGP are negotiated at the time of creation, the BGP speaker can prefix the network layer reachability information. It advertises with an address family prefix. These family include the IPv4 or the default, IPv6, IPv4/IPv6, virtual private networks, and multicast BGP. Increasingly, BGP is used as a generalized signaling protocol to carry information about routes. Sorry, I'm getting caught up in my notes, guys. About routes that may not be part of the global internet, such as VPNs. So to make decisions in its operation with peers, a BGP peer uses a simple finite state machine. If you look in the corner, you can see how this works. Moving on, we can see how this works. Alright, so continuing on the negotiation, we have 6 steps: the idle state, connection state, active state, open send state, open confirm state, and the established state. So, starting from the top, the idle state refuses all incoming BGP connections, starts the initialization of event triggers, initiates the TCP connection with its configured BGP peer, and it changes its state to connect. Moving to the connect state, this waits for a successful TCP negotiation with peer, sends open message to peer, and changes state to open send. While the active state, so if the router was unable to establish a successful TCP section when it ends up in the active state, BGP FSM tries to restart another TCP section with the peer, and if successful, then it sends an open message to the peer. If it is unsuccessful again, the FSM is to reset the idle state. The open send state listens for an open message from its peer. Once the message has been received, the router checks the validity of the open message. If there is no error, a keep alive message is sent, various timers are set, and the state is changed to open confirm. Speaking of open confirm, the open confirm state, the peers is listening for a keeping alive message from its peer. If a keep alive message is received and no timer has expired from the reception of the keep alive message, the BGP transitions to the established state. And lastly, the established state. In this state, the peers send update messages to exchange information about each route being advertised to the BGP peer. If there's any error in the update message when the notification is sent to the peer, the BGP transitions next. We got security. Alright, so by design, routers running BGP accept advertised routes from other BGP routers by default. This allows for automatic, decentralized routing of traffic across the internet, but it also leaves the internet potentially vulnerable to accidental or malicious disruption, known as BGP hijacking. Due to the extent to which BGP is embedded in the core system of the internet and the number of different networks operated by many different organizations, which collectively make up the internet, correcting this vulnerability is a technicality and economically challenging problem. So we have extensions next. An extension to BGP is the use of multipathing. This typically requires identical MED, weight, origin, and AS path, although some implementations provide the ability to relax the AS path checking to only accept an equal path length rather than the actual AS numbers, and the path being expected to match too. This can be extended further with features like Cisco, which enables a ratio of traffic sharing based on bandwidth values configured on individual links. Is it obvious I'm reading this from the notes I've written down? Anyways, keep it moving. We got multi-protocol extensions for BGP, but this would be called MBGP. This is sometimes referred to as multi-protocol BGP or multicast BGP, and defined in IETF RFC 4760, an extension to BGP that allows different types of addresses known as address families, as we brought up before, to be distributed in a parallel. So whereas standard BGP supports only IPv4 unicast addresses, MBGP supports IPv4 and v6 addresses, and it supports unicast and multicast variants of each. Next, we got the uses. Sorry guys, this is almost over. BGP4 is a standard for internet routing and required of most internet service providers to establish routing between one another. Very large private IP networks use BGP internally. An example is the joining of the number of large open shortest path first, or OSPF networks. When OSPF by itself does not scale to the size required. Another reason to use BGP is multi-homing a network for better redundancy, either to multiple access points of a single ISP or multiple ISPs. And it looks like that's all the time I got for you guys today.